Okay, so we've talked about finding centroids. We've talked about how when it's a symmetric system, you can use some aids to find the centroid of a symmetric system. We have these tables that give us some information. We have these various things that we can do, and eventually, unfortunately or fortunately, we're going to eventually have to figure it out. We just don't know what it is, and we're going to have to find it. And that's when we determine the centroid by integration. Okay, so we talked about right here, right? X bar a is equal to the integral of x dA, where you can use this to find the centroid. You divide through by a, and boom, there you got x bar. Okay, but what is dA? dA is really a double integral, right? For any little element, a dA is a little portion in dx and a little portion in dy. So it's a double integral of x dx dy. And it's true for y, it's integral of y dx dy. But the thing is, we don't want to do a double integral. And so it turns out that if you define a little strip in a correct way, we can actually drop this double integral back down to a single integral, and it ends up being x bar a is integral of x bar of the little differential element, and we'll show you that in just a second, times dA, and y bar a is integral of the y bar of the little differential element dA. Okay, so let's look at some examples of picking good little strips. Okay, so we have a vertical strip. Now, quite frankly, this is one that I use the most often, and I'll explain that a little bit more later and in class, just because the equation is often given to us as y is equal to some function of x, and so it makes it easier to do it this way. So we want to define a little differential element, a little strip, a rectangular strip. So this thing right here is our differential element. So how do we define dA? Well, dA is a thickness of dx and a height of y, right? As it goes along this, it's a height of y anywhere along here. So dA is y dx. And we want to integrate x bar, the element of this differential element. Well, where is the x bar of this little differential element? At any point in time, it's right in the middle of this differential element. The thickness becomes so infinitesimally small that x bar of the element just is x. So x bar area is it's integral of x bar element dA, which is integral of x times y dx, and then you plug in y, some function of x, and you can solve for x bar. Now for y bar, let's look at y bar. We're still using the same dA, right? So that dA is still the same as y dx. Well, what is y bar of this little differential element? At any point in time, no matter where it is, remember this. What is this differential element? It's a little rectangle, so it makes it really easy. We know exactly where the centroid is. It's in the middle, right, of the rectangle. So the y bar of the differential element is always right halfway between here and here. Well, and this is 0, and this is y, so therefore y bar of the differential element is y over 2. So then you can solve for that way. That's with the vertical strip. Okay, let's do the same thing with the horizontal strip. Okay, now we're going to define our horizontal strip like this. Well, look at our horizontal strip. What is the thickness of it? Well, it's y, right? It's dy, sorry, it's dy in this direction. And how big is it in this direction? Well, the way we drew this here, it is from here to there. So it turns out that this whole distance is a, and this is x. So therefore, this distance is a minus x. So our dA becomes a minus x times dy. Now, where is the x bar of this differential element? It's going to be right in the middle. Same deal, right? So how do we figure out right in the middle? Well, it's going to be this x distance plus half of the distance from here to here, because that's, it's going to be however far you are here plus the centroid is halfway, so it's going to be half of that. So it ends up being x plus a minus x. So remember, this is a minus x over 2. You can simplify this. This is a little thing that they do in the book, and they never justify it, and it used to drive me crazy until I worked it out this way. But x plus a minus x all over 2 ends up being equal to a plus x over 2. So to me, this is the easier way to see what's going on, but this is definitely the easier way to solve the math, to do the math. And so it ends up being that your x bar of the element is a plus x over 2 times your dA. Your y bar of that element, where is your y bar of that element at any point in time? Well, it's just simply at y. And so your y bar of the element is y, and your dA is the same. So that's how you do the horizontal strip. So, and then lastly, you can do radial strips if you're given r thetas, and you can look through there. It's the same idea. So let's do an example of this. This is example 5.4 in the book, and we're going to determine by direct integration where the centroid of this thing is.